So we are going to resume. The idea would be to, on this axis here, to change the leaves using the model that we described just before, which is the sweep model. That is constructed according to different curves and one function, two curves and one function. We will come back to the precise way how it is constructed later on. So for the moment, we assume that we know how to write this, a sweep with, as a parameter, the two curves, the function, and some, so the two curves here, two curves, the function, and then two parameters related to the size of the organ. And before this, I will remind you what are the different ways to turn the turtle in space, because this will be important in order to position correctly the leaf. So reminder, if you want to turn the turtle, so I am the turtle. This is my left of the HLU. This is my up direction. Sorry, this is my head direction, and this is my up. Okay. If I have a slash, it means that my up is being here. I will turn around my up. So I turn like this. If I have, how do you call this? End. Sorry? Okay. End. Let's say end. 1%. Okay, 1%. If I have 1%, then I will turn in the direction where I bend forward or I bend backward. And if this is this one, I bend forward. So still I have my my frame in this direction, and I would bend here, meaning that I turn around my left, the green one. Okay, and if I have a plus, it was a bit more difficult for me. Turn like this around the direction that is my my back, that is pointing across my back. Okay. So you just need to figure this out and try to imagine. It's a bit of gymnastic, but you need to imagine this at the place where the turtle is supposed to be, and then just make this move in order to obtain the right next move for the organ. So for instance, if you want to bend back a leaf, so if you load the sweep model and you don't do anything, it will arrive in the 3D scene in this position, along the head of the turtle. So if I want to bend backward the leaf, what I would do, backward is this one. I bend backwards, so I will turn in the positive direction, in the direct direction, the turtle head around the left side, like this. Okay. Of course, if you put a minus, you go opposite direction. And now you have the different ways to turn the leaf. So I propose that you do this in your computer so that you get a bit familiar. And just use, because for instance, for plus, you would have minus sign that goes the negative way. And there is also a caret to go in the opposite direction. I propose that you stay with three symbols: the slash, the end, the plus. And you can, of course, you can combine them to make a double change in the orientation of the leaf. So in 3 dimensions, it's super important to master these different ways of bending. But think there are only 3 commands: the slash, the end, and the plus. And you just need to be a bit familiar with this. Okay? So just to try to get this into your hands, check that you can reproduce this type of movement in the computer. And then we pass to this one, where you will you will replace the simple structure of the plant, of the leaf, by this sweep model, a bit finer model that is made from curves. And then you will collapse the stem so that you get this type of structure, showing that, for instance, you could make an ananas from the tail of an ananas, just based on this type of thing. Okay? So I leave you a couple of minutes for this, or it's already done, maybe?
Collapsing is just reducing the internodes, no? Is it that or?
Collapsing is just reducing the internodes. So you find a way to reduce the internodes, either homogeneously along the stem or with more complex law.
So dividing the 10?
Dividing by 10? Yes, exactly. Yeah, yeah.
Or maybe we can make a function to...
Or you can make a function to control this. You can try. I mean, now you are a bit familiar with this type of... try different ways. You can also change the phyllotaxis angle, because once you collapse everything, you see the object in a bit different manner. Then you can change the phyllotaxy and see how it will behave. The phyllotaxic angle, the divergence angle. And here, what I'm going to do, look, this is very interesting. I can modify at once, because all the leaves, they are the same model. And this is controlled with, a single curve. And for instance, this curve controls the width of the leaf. So just by moving the curve, I can make it very different in terms of impression. Again, you see how important is the geometry of the stuff in the perception of the entire object. And again, most probably, this is due to the fact that when I change the geometry at some locally, it is multiplied everywhere. This is why it is so striking, the change. One thing that you can do also would be even more impressive, I think, for if you want to make a function, is to make a function that would change the insertion angle here. So you have the leaf. It is controlled by probably an end. The inclination angle is controlled by an end. If instead of putting a constant value, you put a function of the rank of the edge, it may give the impression that the stem really opens the leaves. Okay. Or you can link with the graphical object.
The insertion point is the phi, what do you mean by insertion point?
Insertion angle.
Angle, okay.
I mean this. I will draw it for you. So you have the main axis, and then you have the leaves. They could be very sharp angle at the beginning, and then progressively open like this on both sides.
Okay.
Oh, sorry. Just something like this.
Okay.
Okay, so I think most of you have made this example. So we will finish the series here with a small, this exercise that we were mentioning before. If you have your leaf position naturally without doing anything, the leaf will be placed here at the center of the internode. What we would like actually is to have a leaf, but at the periphery here. Okay, so you have your radius r. Okay, so how would you, so this, I will leave you like 1 minute to think about this. How would you, so my leaf is here. I want to put, my leaf is here. I want to put it exactly in the same position, but shifted by a small amount. How would you do? So imagine that the turtle is arrived at this point, which is just after the F here. Now, if I want to make a leaf, a lateral leaf, I need to have a bracket. So this is the first point. Second point, I need to describe where should I put the leaf according to this point. If I don't do all this, and I do just this, it will make this drawing with the leaf inserted at the center of the cylinder, at the exact position of the current turtle. So in order to shift the turtle, I need to make a shift operation. So this is a shift operation. And the shift consists of what? It consists of bending. Actually, we should replace this by like this, because I said that I should bend. Okay, the turtle is. I should bend forward by 90 degrees, move forward without making any cylinder. This is why it is small f, by a radius, which is the r, and then bend back from the opposite angle to my original position. And now my turtle, she was here, and now she is, after this statement here, she is here. And now I can draw my leaf by bending by 45 degrees first, and then by producing the leaf.
It's just during the shift operation, the first shift, the first bending and the last bending. So I don't know the point of it. Why not just doing a FR and then you shift? Why do you need to make the...
This one?
Yes.
Because if I am here with my frame, turtle frame here, HLU, okay?
Yeah.
If I don't do this, I just do a F, I will move in this direction because the head is here. I will move from a radius in this direction, so I will be here.
Okay. Yes, it's to specify where the radius.
So if I want to change momentarily the direction where I move, I need to open the bracket. This is the momentarily. Change my direction, move in this direction. So it's really like a small robot, you know?
Yeah.
Okay? And then if you do this, you correct the position, and then if you make this modification, actually this exercise or example 04D, you would have the leaves inserted at the right place. And I think this is one of the complex examples to position the different things relative to each other in such a branching system. If you know how to do this, you will know how to do many other things. Okay, so what you could do is to, oh yes, sorry, just a last point about phyllotaxis. Instead of using rules and production rules to produce the stem, what you could do is produce the whole stuff embedded in the axiom. So this would be a way to create an initial state of your plant. How I would do this? I would simply make a loop that produces an internode, that produces a leaf between brackets, so a lateral leaf, any number of times, n times. And by doing this, I am simply doing essentially the same thing as before, but instead of using the L system production rules, I am using L system production rules, but only in the axiom, which avoid to have this the further description of the model polluted by the construction of the initial model. Okay?
It's more readable.
But, well, this would be to separate what I consider to be the initial state of the system. I want to have it in the axiom from after the production rules that will say how the model should evolve in time. Okay, so this would be to separate these two things. Okay. Now, we are going to speak about branching, because this was the position of the branches, of the lateral branches, but we didn't say how the branching patterns should occur. So we are going to speak about branching mechanisms. As you remember, what we said in the first course is that branching can be of different types. And there are two main patterns in plants. You may have what is called diffuse branching, where leaves or branches will occur in a sort of homogeneous manner, homogeneous density all along the plant, all along the stems. But the branches can be also clumped. And you see that groups of leaves will appear and then followed by groups of empty internodes. And the question is how to model this. And the idea is that, okay, now we are a bit in terms of stochasticity in the system. And we want to find a model that would be able to, as simple as possible, but that would be able to produce this type of patterns just by changing parameters of the model. And one model is very well suited to this. It is called Markov chain. It's a stochastic process model. And I will show you how it can be used in the system. And you will see that it's not very, I hope, that it is not very difficult. So, imagine that, let's set up the problem. Imagine that I am on a stem and I am at a node K. And the question is whether on this node I will see a leaf. Let's say that the lateral green stuff are leaves. It could be branches as well. And I will say there is a variable that I call xk that will take the value 1 if the node is branched, if there is something on the node, and take the value 0 if this is not the case. Okay? And the question is, how can I describe the probability to obtain a certain leaf at a given node? It may be that the probability is simply a constant number. And then, if I draw a constant, with a constant probability a leaf, I will follow can you remind? Because it's... Sorry?
The bit diffuse branching?
It would be like tossing a coin with the same probability all the time.
Yeah.
So what sort of law you get from this? The total amount of success that you have. Binomial distribution. Okay. So, and this is the case where there is at some point in the tossing of the coin, or in the deciding whether there will be a node, a branch, a lateral leaf or not. This is a case where I don't pay attention to what occurs before in what I was drawing. And this would be very constrained, because I would have always binomial distribution. Okay. Now I want to be a bit more specific. So how do I do this? Well, I need to decide whether these two things are equal or not. So I read this for you. What is the probability of, at node K, observing a leaf, knowing that at the previous node, I observed no leaf? So at the previous node, I observed no leaf. Okay? If this probability is not the same as What is the probability of observing a leaf? Let me see.
If at the previous node you have a
Yes, if at the previous node you had a leaf, then the probability to observe a leaf actually depends on the node before. So I need to take the node what occurred on the node before into account. Okay, and if you have this, if this is not equal, then you have a property that depends on the memory of the system, on the past. Okay, and as soon as you enter into this, you enter into the Markovian type of processes. If we make the system as simple as we can, we say that this probability doesn't depend on time, doesn't depend on the rank of the node here. It's really independent. So it's a constant. So instead of having the probability of tossing a coin that is constant, it's the probability of tossing a coin knowing what was the result of the previous one. It's a bit more complex, slightly only. And then what I say is that the probability of observing a leaf knowing that there was no leaf before, or the probability of observing no leaf knowing that was no leaf before, are described by two constants that corresponds to the probability of these events. And of course, the probability of observing no leaf knowing that there was no leaf before, it would be 1 minus this one. The probability of observing no leaf knowing that there was no leaf before is, the probability of observing one leaf showing that there was no leaf before, it's 1 minus p00. So there are two independent parameters only, not 4, because one is 1 minus this other one, to describe the system. So it's a bit more, so if you don't take into account the memory, you have only one parameter, which is the probability of tossing the coin, which might be biased towards, it's 70% against 30%. So this would be the simplest case, but with this, you are constrained to observe binomial distribution, and then the pattern will be always the same. If you want a bit more complex system, and you will see that this will make the possibility to observe different types of patterns, then you need to introduce two independent parameters that will control the system, and this is the most simple model, more complex model than with memory 0. Questions about this, or is that okay for everybody? And you will see that it can be implemented, all this can be implemented in IPy extremely simply. So we will see. So now I have my two independent numbers. This system can be represented by this graph. Can you all see why? So this is the state to have 0 leaf. This is the state of having 1 leaf. What this diagram says is that there is a probability, if I am in a 0 leaf state at node k minus 1, I can live with the probability p00 in this state of 0 leaf. So the probability to remain empty is p00. The probability to get to the other state is, of course, 1 minus p00, and it's called p01. Okay? Yes? Arthur?
But it's not enough to know P01 and P00.
No, it's not. So this one is 1 minus this one.
Yeah.
Yes. And now I need to give the other probability, which is P01, so this one, which is the probability to, sorry, it's a P11 here. Yes, I'm sorry. So it should be P11, which is the probability to loop to stay, when you are a leaf, to stay a leaf at the next node. So you must correct this. And then this P10 should be the 1 minus P11. Okay? And what is interesting, you can, from this, compute the probability of branching. So, because we are interested not in the probability of giving a branch knowing that where I was before. I am interested in the overall probability of having a branch in my system. And if you make the computation, it's quite easy. You find that this probability of getting a branch not knowing anything. Well, actually, it's the probability of getting a branch. It's the probability of getting a branch knowing that I was in the state 0, plus multiplied by the probability of having the state 0, plus the probability of having state 1 and keeping is, and switching from state 1 to state 0, multiplied by state 1. Okay, so you would write this, and with this you would extract the probability of having state 1, and this would be simply solved by this equation. And with this, what you can see is that the parameters of the system control the probability of a branch. And when you do this, what you observe is that by just selecting different numbers here, and that are different, so a couple here that is different from this one, but such that the probability of branching is the same. So I have 0.25 probability of branching here. I've also selected this number so that I have also probability 0.25 to have a branch here. And what you observe is that the behavior of the two systems may be drastically different. One is more diffuse, and the other one is more clumped. Okay? Showing that just because you could imagine many ways of modeling this clumping effect, etc. But what we want to have is sort of grasp one simple way. So although there is a bit of math, it's still quite simple because it has only two parameters in the system.
How well does it describe
Yes.
reflux?
Yeah.
Yes. Well, actually, this type of models have been tested, and in particular, my late colleague Yann Guédon was a specialist of this type of models applied to the description of branching on stems. And he was doing this largely with Evelyn Cost, with a former colleague of mine as well. And they described the branching structure of fruit trees in particular, but not only fruit trees, could be also spruce trees or conifers, and potentially many types of trees. And they were able to show that not exactly this model, because this model is super simple, but variants of these models, I can explain this to you a bit later. Just light variant of these models are quite well grasping the branching patterns of rather complicated patterns of in plant systems. Actually, I have yet another model, slightly more complicated than this one, that I can show you. But I will show you after you look at the L system corresponding to this, because the point is to understand how you would represent all this in an L system, and it would be quite easy. So I sort of schematized what occurs here. What you say is that let's look at the production rule. So now we enter the domain of non-deterministic L systems, meaning that I will have rules, different rules, to rewrite the different symbols or modules in the system. Okay? Now the idea would be that I am using this rule, this first one, is producing an internode and an auxiliary branch that is called M, plus an apex. So this one is branch node. This one is non-branch node. So I am in this situation. Where is this one? I imagine that I am constructing my axis. I have already put a number of things below, and I am at this point. And I need to decide what will be the next point. Is there a branch or is there an empty node? And I need to take this decision. Okay? And I have an apex that is growing, and that will either produce the I MA or produce IA. So this is if this is x equal 1, xk equal 1, and this is xk equals 0. Okay, I need to make this decision to produce the actual stuff. So there will be means in the system, and you will see how it is coded, to draw this rule with a probability P11, because if I am in the state 1, I will draw, so A is state 1, B is state 0. So I will stay in state 1. I will stay from A to A. See, if A is state 1, I pass from state 1 to state 1 by a branch. So this is P11. And if A becomes a B, I start from state 1 and I go to state 0. And then this pop up with probability 1, 0. Okay? So there is a way, and you see that's very easy, to draw these probabilities according to these numbers and select the rules according to these numbers. And in this way, just by doing this, selecting the rules with the correct probability, with the probabilities given by the key numbers of the system, the key parameters of the system, then I automatically make this type of Markov chain. Okay? There is one thing that we should add. We need to say in which state we start at the beginning of the system here. Is it a branch node or an empty node in the beginning? And then here, what I say is that there is axiom is S. There is a probability that S becomes a one state, which is P initial 1, 0, 5, and the probability that S becomes an empty state, which is P initial 0, which is 0, 5. So it's half-half to start in a 0 state or in 1 state. Okay, not too difficult. Can you try the example to see how it works in the example?
So when I run it multiple times, I have
You have different
results, of course.
results, of course. If you know how to do to get the same result all the time?
So
Fixing the random generator.
Yes, and you call, so you have a default random generator that comes from the math module, which is seed. Yes, but you could also use the random generator of the NumPy library. That would be numpy.seed, and they are different random generators. Okay, did you try a bit to change the probabilities, for instance? Did you understand how this selection of the rule was implemented? Is it clear to you? Because this is not LPy code here. It's a sort of pseudocode, yes. Well, the point is that can you get to the point where you are not necessarily able to write this on your own straight? Because you need, again, you need to really write the code yourself. You need to get a bit more acquainted and familiar with the code. But on the other hand, if you want to reuse part of the code in other programs, would you be able to understand enough so that you can pick the right part of the code and then reproduce it? This is the question, actually. Somehow, okay.
I don't necessarily understand the random function here, which is called if random.
Yes, random.
In the syntax.
Random returns a number. It's from the library. I don't remember which one I used, but the math library. And it returns a number between 0 and 1 at random. Okay. Ready to pass to the next thing? Depending on you, would you like to go to the hidden Markov models, which is a bit more, not too difficult, but a bit more. Or would you prefer to skip to the next topic? Maybe. Okay, I can just give you the idea, and we don't look at the code. And if you are interested, then you look at the code, and then we can also discuss about this. But I can give you the idea because Kara, I think this was you. No, who said that whether this reflects the actual distribution of branches in plants? Yes.
No?
Yes. So there is a whole bunch of things that we need to know about how stochastic process may represent the actual patterns in plant. One of the limits of this model, of this simple Markovian model, I think you can remember this point, because if you want to have a bit to remember something about this. So you have the model with state 0 and state 1, with the probability of staying in state 0, probability of staying in state 1, and probability of passing from one state to the other. Okay? The fact that we have the probability of staying in state 0, the probability of leaving state 0 is P 0, 0 after n turns, multiplied by the probability 1 minus P 0, 0 once. So it's probability to stay n times in. So the probability to stay n times in state 0 and to leave after n times is P0, 0 at the power n, multiplied by the probability of leaving the state. Because of this, you see that there is an exponential law here. The law for leaving the state is a decreasing law, exponentially decreasing law, which is the law that describes how much time I will stay in the state. In plants, it's not always the way it goes, because you have more. The more you stay, the less probability you have to stay. Okay, it's not always. It can be in plants. Can be that you have low probability to have to stay very short, high probability to stay medium term, and then low probability to stay long. So it may be more like this. So if you replace these laws related to this probability of staying in the state, you remove this and you replace by this, you have a semi-Markov model. And this would lead to more realistic patterns, because you can tune this as you wish, because this is the actual law that you observe, that you stay in the system.
Why semi-Markov?
It's semi because you make a trick, which is you remove the dependency internally. Internally, you don't rely on the previous state only. You rely. It's a more complicated thing. So it's semi-Markovian. Okay. And finally, there is the hidden Markov models, which are more adapted to plant as well. And you have semi-hidden Markov model, combining the two things. If I find so the idea behind Markovian model is that hidden Markov models is that the lateral production, I may want to describe the state of the meristem independently of what is actually occurring at that node. I want to consider that the state at node K is not whether I will have a branch or not. It's just a state that will describe the state of the meristem while I'm going through the system. And then what I'm going to observe will depend on this state. So the idea is a bit slightly different or slightly augmented. My meristem would go in this way, will pass through state 1, state 2, state 3, state 4, I don't know, something like this. And the probability to observe a branch here will be the probability of x equal 1, knowing my state equals 1. The probability here would be probability of observing a leaf, knowing I am in state 2. And you see that if I am using this, I can change my probability according to the state now. I introduce additional parameters in my system that makes it more flexible to describe complex patterns. Is that clear. And there is a huge step made here, because x before was necessarily a scalar value or even an integer in order for this to be discrete. Okay? The states here, they are discrete elements. Here, the state on the axis, which is a bit abstract, is discrete, but the observation here can be continuous variable, like a length, like a radius, like it can be also number of flowers, can be whatever you can imagine about the variable that you observe. So you decouple a process that is stochastic, that is hidden, that you don't see. It's a sort of assumption about what is behind. And what you observe is something that depends on the state that is hidden. Okay? And with this, you are able to, for instance, to define at each node several, so this can be a vector, several variables. One describing the radius, one describing the length, one describing the fruit number. Okay, each one corresponding to one distribution, observation distribution in that state. Okay, I don't expect that you grasp all the stuff, but just to know that in the family of stochastic model, you have this type of variation, this type of family of variants of models. Okay, any question about all this? And we jump to the other. Let's see, it's we can yeah, we can try to get to the end of this branching segment before we make a pause. Tired? Or you prefer to make a pause? No, maybe a pause now would be okay. What do you prefer? No, you want to continue?
Yes, but I don't know.
Okay, other ones? Continue. Okay, sold. Okay, so this was a way to model the branching. So now we want to simulate the continuous development of axis so that we can have this type of simulation and see how we can induce branching patterns that would come from the continuous growth of an axis, okay, like this one. In order to do this, we are going to follow this scheme. First, I remind you that the rules are a bit like, actually they are not a bit, they are evolution equation of the system. We are going to make them depend on time increment so that the evolution actually represents the progression in time. How to integrate the equation? Well, actually, it's very simple in LPy. You just you make derivation of your system, so applying the rules one after the other. And you need to model, if you want to have a description of the growth of your organs, you can use two ways. First way is to do as we did before. So you have a local length of your internode at some time, and then you add a small increment. So this would be the equivalent to a differential equation. You have the small increment and small increment, and then you integrate. Another way to go is to say, I know that the development of my internode will follow a rule, a law, and I will just keep track of the time, of the age of this internode, and then plot the length of this internode as a function of this as a function of this curve that describes the growth law of this internode. So here I assume that I don't know exactly that it's not by the increment that I will describe the growth. It's more that I know the law. I know that internodes are going to have sigmoidal growth, and I will just follow according to a time. Tracking the age of this internode, I will just follow the rise of the length in time. Okay? So there are two ways. One that would be, let's say, incremental, and the other one that would be let's say, global description. Okay? And this is the type of law that you have through global description. I put here a law that I'm using when there are no constraints to describe sigmoidal growth. So it's a Hill function. It comes in this way, and there are a few parameters. There is the starting value, so the minimal value that let's say the internode length will take. There is the maximal value that will be the minimal value plus a parameter that is b. There is a shift in time. There is the mid-time value. So the value that is reached at the when the development has reached the half of its total development. So this is TA, this is here. And there is a shift here, T0, that describes the moment where the function will start to grow and to apply. Okay? So I entered this function in the system, and you can use it as a sort of typical sigmoidal rule in your system. You could use logistic rules, you could use arctangent rule, you could use many other types of functions. This is I like to use it because the parameters are easy to control. Okay. So if I want to create a continuous growth, I have basically three ways. First way would be to count time in the system. So this would be represented by a variable t. And then each time that I advance one step in my derivations, I increment the t by a small dt. Okay? This would be one way to count time. Each particle, each apex, each module is keeping track of the global time. I could also have a global variable that would represent time that I will increase also. This would be another alternative way. But in all the cases, it is a global time that starts at 0 and then progresses on the flow. And then if I want to say there is an internode, because I need to take the decision, I produce an internode, because otherwise the internode is just growing but not producing any event, any botanical object. So I need to have a moment where there is a decision to create an internode. And this is where it goes. And you say that if t, the global time, is a multiple of some period, then I will produce an internode. Okay? So how you express this is a multiple of t is just Python code, and you can find this in the examples. Another solution to create internode when you are growing continuously a stem is to track meristem age. So you'd say that so here I have only time. Here I have time and age. And instead of checking whether time is a multiple of a period, I will decrease a certain I will augment my age, and as soon as the age has reached this periodic value, I will create my my internode. It's a bit different test if you compare these two things. It's not done in the same way. It's done with the same precision. Okay, and the last point is to have a countdown in the system where you start with, you say that I count down, I am an apex, and I will count down the moment where I should produce an internode. So you start with your count at t, and then each time you produce something, you decrease the countdown by dt. And as soon as you reach, so the apex as a countdown state, as soon as the countdown state is less than 0, it's the moment where you create an internode, and then you re-put the countdown to t for the next turn. Okay? Okay, and this is example 6. And now finally, we get to the moment where we can grow the system. We can produce the internodes at different moments in time. And we can make, at each moment where we create an internode, I could also create a lateral branch. And the lateral branch could follow the same rules as the main stem, or slightly different rules that I can modulate. And this is the way we produce a full branching system of a plant that has this sort of continuous growth associated with it. Okay? So I propose that you can check this example 6, and then we finish by the final example, so that it's all done, and then we make the pause. So just look at the example 6. Just check that you understand everything, not everything, but most of it in the code, the important parts. If there is something that you don't understand, please ask. And you see that in this example, the idea would be to control, for instance, the delay of the branching. So the main stem produces an apex, and this apex can start to grow immediately or with a certain delay. And how, sorry?
T0 of the hill curve.
It could be the T0 of the hill curve, or an amount of time like a countdown. So you put, when I create a bud here, I could put a countdown, then the countdown reaches 0, and then it's time for the lateral apex to grow. The point is that if you want to create an extremely more complex plant, in a way, what I gave to you in these examples are sort of patterns. So you can reuse these patterns to build on this and create more complex examples. Okay, so we can skip to the last point of this branching pattern session. This is related to how do you make branching when you have rhythmic growth. So you remember yesterday we were speaking about the fact that meristem, when they grow, the primary growth can be in one flush like this, or continuous flush, or can be rhythmic, like shook, shook by flushes. How would you do this? And why would you do this? So there are two main reasons why there would be rhythmic growth. First is endogenous growth. The plant itself creates this rhythmicity. And second option would be that the rhythmicity comes from an external signal. For instance, winter or summer, so the season. So in winter, everything stops. So you have to have rhythmic growth if you want to survive the winter, to support with rhythmic growth. So here I chose to show you the case of an external signal that would be felt by the plant and that would impose a certain behavior of the growth. So I called this signal external signal, which is quite original. And if you look in the code, the signal is a sinusoidal signal, or cosinusoidal, I don't remember. Okay, so it's to mimic a bit the season, like with a periodic behavior. And what I say is that there is an internode, and this internode has a state which is growing or not growing. It's a Boolean state. Here. If the state is growing, I do some stuff. But if the state, if the state is growing, I do all this. But if the state is not growing, I just continue slightly to accumulate time and age without changing my state, without changing my length, without changing anything. I just accumulate time. Okay. So if I'm not growing, I don't move. I just feel the time that is passing. But if I am growing, I do a lot of things. And among the things that I am doing, so I look at the external signal. And if the external signal is below a certain threshold, my state becomes false, which means that I stop growing. I will stop growing for the next steps. And otherwise, so if the external signal is still allowing me to grow, then if my length is not already the final length of an internode, I will compute the next step of my length by adding a bit of length according to what I feel as an external signal. So if the external signal is high, I will grow fast. If the external signal is low, I will grow slowly. And this results in this type of rhythmic growth. And you can animate this on your computer, and you will see that the plant the axis is growing fast and stops, then resume the growth and stop, and resume the growth and stop. Can you play this on your computer?
Yes.
Yeah. So can you have a short look at the rest of the code so is this clear now, this part of the code? So you can look at the rest of the code, look if everything seems consistent. Again, 1 minute, and then we add branches on this.
So, just you explain maybe I didn't follow it. You explain why the growing stopped. It became very very slow at the moment,
Yeah.
and then
Yeah.
continue.
Yeah.
So what explains this effect?
Yeah, the fact that I multiply, so here there is the increment of growth in the internode, and I compute the increment of growth as a growth rate. Actually, the growth rate is modulated by the external signal. If I put external growth rate together, it means that the growth rate is controlled by the external signal. So if the external signal is high, like temperature is high, then the growth rate will be high. And if the external signal is low, then the growth rate will be low, and this will change the pace at which the internodes are growing. Is that clear?
Yes, yes.
Okay. Okay, so then we can add in the final step branching on this rhythmic structure. And you will see that you can do this in different ways. The branching can be immediate, meaning that each time an internode is created with a lateral bud, the bud will grow out immediately without delay. You can do this, but with a delay. Each time there is a bud, the bud will keep quiet for a certain amount of time that is controlled. And then after some time, it will start to grow out. And you can do this with a delayed, but in a way that you find in many plants that the pattern is acrotonic. Remember yesterday this definition? So the idea of acrotonic pattern is that the leader apex grows, and due to the season or to internal cues, stop to grow. On the way, the leader was putting a lateral buds, and there is the leader bud here. Okay, and when resuming the growth, all the buds, well, all the latest bud will start to grow out, but the ones that are the closer to the leader will grow more than the ones that are below. You may have also like this. And this pattern is what is called acrotonic branching pattern. So how would you do this? Well, this is illustrated in example 06 and D to F, F being the one with acrotonic thing. And the idea is that as soon, so if when this bud was created, it was created with a certain at a certain moment, and then it starts to accumulate a delay. The delay corresponding to this bud. At the beginning, it would be 0. As time is passing, the delay will increment. The delay will become 1, then delay will become 2, then delay will become 3. And when the bud here starts to be dormant, the delay is maybe 4. But the bud here has a delay which is 3 now. The bud here has a delay which is 2. The bud here has a delay which is 1. So all the buds that are after this one have a delay which have computed a delay that is less than the one that is below. So when I will start this here, you see that all the buds will start with, but with delayed that correspond to this behavior. To the fact that this one will grow out first, the second one will grow out in second, etc. Okay? So you see the type of reasoning, the type of tricks, the type of patterns, design patterns that we are using. It was a bit to show you all these elements. Okay, so we can make a break here, I think. Thank you very much.